Good morning. Today we're going to talk about section 4.4, multiplication rule, the basics. You recall from section 4.3, section 4.3 talked about the addition rule, and as we recall, the addition rule was used to compute probabilities in OR type situations. Alright, today something new, section 4.4 multiplication rule, and in section 4.4 multiplication rule basically handles AND type situations. For example, let me give you a simple example here. If we've got a 2-question quiz, and in this quiz there's a true-false question followed by a multiple choice question with 5 choices. And I ask, what's the probability that both questions are correct if a student takes random guesses on both questions? In other words, we want the probability that the first is correct and the second question is correct. Let me write that down. Let's say a student makes random choices for both, and I'll say find the probability that he gets both right, that they get both right, that both questions are correct. Alright, well, I suppose I could rewrite that event that both are correct, rewrite it and say that's equivalent to that the first question is correct and the second question is correct. Alright, so we've got an AND type event here. Well, that means that they both have to occur simultaneously. Let's see, the probability the first is correct. Let's see, if we draw a tree diagram, if I look at the possible responses or outcomes for the first selection and then tail them off, each of those can tail off to 5 other selections for the second question. I can clearly see there's 10 possible paths from left to right, hence there are 10 possible outcomes for this quiz paper. True A, true B, true C, true D, true E, etc., all the way up to false E. So out of these 10 possible outcomes, how many correspond to both questions being correct? Well, only one of these outcomes, true A through false E, have both questions correct, so I claim the probability is 1/10 or 0.1. Alright, let me suggest to you perhaps a shortcut way rather than listing the sample space brute force as we've seen. That may be a cumbersome way to handle some harder problems, so I'm going to suggest to you a solution that looks like this. Let's say I'm looking for the same thing. Let's see, I'll claim the probability that the first is correct and the second is correct is, well, let's see, I'm going to say it's the probability that the first is correct times the probability that the second question is chosen correctly. Let me suggest that to you. Well, the first question is a true-false question, so the probability of that being chosen correctly is 1/2. And the second question is a multiple choice question with 5 selections. So that's going to be a 1/5 probability, and 1/5 times 1/5 is 1/10 or 0.1. So I get the same answer as I got in the brute force method. And this suggests a rule to handle AND type situations, and we call that the multiplication rule. multiplication rule says this. The probability of A and B is the probability of A times the probability of B, but there's an important disclaimer if A and B are what we call independent. Independent events. Okay, if they're not independent, we have to make some adjustments here. We'll see an example of that soon. Let's get some terminology here down. I'll say A and B are independent if the occurrence of one does not affect the probability of occurrence of the other. Alright, so clearly we can see these two questions in this above example. Well, the event of choosing correctly is independent. Assuming random choices are made in each question, certainly the probability of getting the multiple choice right is not affected by the event of getting the true-false right, and of course vice versa. Alright, let me suggest to you an example. Exercise. This is exercise 1 out of the book. Exercise 1 in section 4.4. This is on page 158. Well, they talk about that drug use chapter problem where people did or did not use drugs, and the machine said they did or did not use drugs, and you'll hopefully recall the numbers here. There were 1,000 people in the study, and they broke down cross-reference in this table-like fashion. Alright, let's look just at the subjects who use drugs. Let's look at the subjects who use drugs. And those are signified by capital D, right? And if I just focus in on that row, I can summarize that row just like this. Zoom in on that row of drug users. Alright, so the machine caught 44 of them, did not catch 6 of them, and that's how this study broke down. Alright, if from this scenario here, if 2 of the 50 drug users are randomly selected, I'll say chosen, let me call with replacement, find the probability that the first choice was a positive result. In other words, the machine caught him, and the second had a negative result. Right? So we're in this scenario here. We've got 50 people, 50 drug users. We're going to pick 2 of them randomly with replacement. That means the first choice is thrown back into the pool and available for selection again in the second selection. All right. With replacement is kind of a code word for independent events. Let me write that down. With replacement, that implies independent selections. I think you can see that if we pick somebody from this pool and throw them back into the pool available again for a second pick, well, the probabilities of picking, well, under any condition, the probabilities are not affected. So I can write this down like this. We want the probability that the first selection is a positive result and the second selection had a negative result. Alright, because of independence, I can claim this is then the probability that the first is positive times the probability that the second person chosen is negative. The probability that the first is chosen positive is, of course, 44 out of 50 times, well, what's the probability that the second selection has a negative result? Well, because we are doing it with replacement, the second selection, we've got the full number of 50 subjects available for that second selection also, and the probability of getting a second one negative, and that selection, it's going to be 6 over 50, and if I punch this out, this is 0.106. Okay. Alright, let's try the same problem. Again, we want 2 of 50, find the probability that the first is positive and the second negative. Let's do it without replacement. Let me put this in a different color. I'm going to ask the same question, but without replacement. Alright, now when you're making selections without replacement, well, things get a little bit more difficult. Not independent selections, and what we have to do is make some adjustments in our multiplication rule formula. Again, same situation here. I'm going to ask, we'll randomly select 2, but without replacement. Right? And I ask, what's the probability that the first selection is a positive machine result and the second one is a negative machine result? Well, the probability that the first one is positive, well, in our first selection we've got 50 people to choose from, and if we consult the table, the 44 of those had a positive result, times without replacement. Well, if you're doing things without replacement, that means the first person chosen is not available for a second selection, so our sample gets reduced by 1, and we've still got 6 available for 6 negative results available for a selection in the second selection. So if I punch this out, 44 over 50 times 6 over 49, it's 0.108. Alright, so we can see that our probability does change slightly in this case when I change from a with replacement scenario to a without replacement. Alright, well, the moral of the story is, if I'm looking at the probability of end type events, well, the multiplication says this. The multiplication rule says this. The probability of A and B is the probability of A times the probability of B, but informally we must adjust the probability of cascading events down the line for not independent events. Okay? Alright, as we did here, we made a little adjustment in that second factor in that without replacement scenario. Alright, I'm going to extend this multiplication rule to handle more than one event, more than 2 events. Let's see, multiplication rule. I'm going to say the probability of A and B and C, if I'm talking about intersecting 3 events, Well, it's easy enough to prove that it's going to be the simple probability of each event multiplied, again, if A, B, and C are all independent. And if they're not, well, we've got to make some adjustments in those second and third slots. And I can play this game ad infinitum. Dot, 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 for any number of events. Dot, 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 multiplied by the probability of any number of events you've got intersected there. Alright, so what I'm going to do is look at example 2 on page 159. Let me get a fresh screen here. Example 2 in our text on page 159. It says this. Let me turn there myself. Give me a minute. Page 159. Alright. I'm going to go ahead and read the problem. Example 2, page 159. Airport baggage scales can show that bags are overweight and high additional fees can be imposed. The New York City Department of Consumer Affairs checked all 810 scales at JFK and LaGuardia airports, and 110 scales were found to be defective and ordered out of use. Okay? Let's look at parts A, B, and C. We're going to look at all three parts here. Part A, if 2 of the 810 scales are randomly selected with replacement, find the probability they are both defective. Let's look, part A. If 2 of the 810 are randomly selected with replacement, find the probability they are both defective. So, probability that both are defective. I'll label that with a cap D here. Well, we're picking 2, so I want the probability that the first is defective and the second is defective. Everybody agree? Well, we are making selections with replacement, so part A specifies with replacement, which means independent selections, right? So I can say this is the probability that the first is defective times the probability that the second is defective, can't we not? And let's see, I've got 810 scales here, and 102 of them are defective. And because I'm doing things with replacement, the probability in the second selection does not change, independent events. And if I multiply 102 over 810, well, that's 102 over 810 raised to the second power. I get 0.0159. Hang on, let me check that. 102 divided by 810 raised to the second power, 0.015, we'll call it 0.0159. Okay, I put a box around that, and I'll call that the answer to part A. Alright, talk about part B. Part B, well, let me read it. If 2 of the 810 scales are randomly selected without replacement, find the probability they are both defective. So, same or similar question really, except the scenario is without replacement. Alright, so I want the probability that the first is defective and the second defective. Well, remember, you must make adjustments in selections down the line if you're talking about AND events here. Well, the probability that the first is defective, well, of course, that's going to be 102 over 810 as in the part A, times, well, we must adjust for not independent events. And if you're doing things without replacement, the trial selections certainly are affected, right? Not independent. So I've got, well, let's see, I've got one less to choose from if I'm doing it without replacement. And assuming the first event has already occurred, you've got one less defective one. So notice the second fraction changes from part A to part B. And I punch that out, I get 0.0157. It changes. Maybe not a whole lot, but it does change. Okay, so part A with replacement, part A without replacement. Alright, let's look at part C. It says a larger population of 10,000 scales includes exactly 1,259 defective scales. Alright, let's take a look at this. Same example, part C. Alright, we've got 10,000 scales. And of those 10,000 scales, we claim that 1,259 are defective. Alright. It says if 5 scales are randomly selected from this larger population without replacement, find the probability that all 5 are selected. So 5 are picked randomly. Okay. I want the probability that all 5 are defective. Alright. I'm going to describe this as an AND statement. Well, it's the probability that the first one is chosen defective and the second is chosen defective, and I'll just do ... all the way up to the 5th is chosen defective. Alright, now we are choosing these random selections without replacement. And again, if you're picking things without replacement, that means the events are going to be, selection is going to be affected, and we have not independent events. They're not independent. Alright, so I claim I can rewrite this in this way. It's the probability that the first is defective times the probability that the second is defective times the probability the third is defective times the probability that the fourth is defective times the probability that the fifth is defective. Right, but again, you must, because we are choosing things without replacement, we must adjust the probabilities of these events as we go down the line. Alright, the probability that the first is chosen defective is going to be 1259 over 10,000 times, well, assuming the first one has already been chosen defective, our available pool goes down by 1 and the number of defective units goes down by 1, and I'll do this right down the line. 9998 in denominator, 1257 in numerator, 9997 in my denominator, 1256 in the numerator, and assuming the first 4 have been chosen defective, well, the probability that the fifth one is defective is going to be 9996 over 1255. Alright, now if I punch this all out, and it does take a while, I get 0.000314. And our book makes the comment, yuck. Well, it is a lot of button pushing. Alright, so there's our final answer. Making the necessary adjustments for the not independent events. But I'm going to ask you to notice something. Note. Suppose we assume independent events. In other words, assume it's with replacement, even though it's not. Let's see what happens. The probability that all 5 are defective. Well, it's going to be the probability that the first one is defective. Well, all these other probabilities will be the same if I'm with replacement. So basically I've got the same fraction multiplied by itself 5 times. And if I punch this out, I'll get 1259 divided by 10,000 raised to the 5th power. I get essentially the same answer. It does not exactly the same answer. Write it down. On my calculator, I get 0.0000316, which, for all intents and purposes, is pretty darn close to my original answer. But of course, this value was a lot easier to get, a lot less work in punching numbers in my calculator. Alright, so what the book is getting at here, they're saying that it's okay to assume independent events. It's okay to assume with replacement under certain conditions. It's a bit of a trade-off. You don't get the same exact answer, but good enough for most intents and purposes. The book talks about a 5% guideline. The 5% guideline says this. Well, it's cited on page 158. It's written out real nice in the book for us. It says this: if the sample size, and here it was 5 in this last example, if the sample size is no more than 5% of the population from which it's drawn, then we can treat selections as independent, even if they're not. In other words, we can assume you're doing things with replacement, even if the problem specifies you're not. Okay? We can assume things with replacement. Now in this example, our sample size was 5. We were taking 5 from a pool of 10,000, and certainly that is not more than 5% of 10,000. 5% of 10,000 is 500, right? 10% is 1,000. 5% would be 500. So 5 is certainly not more than 500. So we can assume with replacement in this last part C. Okay? Again, it's not quite as accurate, but good enough when we consider the labor savings. All right. I want to look at now number 15 in our textbook at the end of the chapter and under the homework exercises. Let's take a look at number 15. This is number 15 on page 165. I believe it's on your homework list. They're talking about that pre-employment drug screening test again, the chapter problem again, and they give you the table all over again in that homework section. Let me write it down here. And hopefully these numbers will look familiar. Alright. Number 15 says this: if 3 of the 1,000 test subjects, you recall we had 1,000 test subjects here in this pre-employment drug screening study, If 3 of the 1,000 test subjects are randomly selected, find the probability that they all had correct test results, where correct means true positive or true negative. Is such an event unlikely? Alright, let's take a look at Part A. Part A says they want us to assume the selections are made with replacement. Alright, so we're looking for the probability that all 3 had correct test results. Let me write that down. We'll randomly select 3 from the study. Find the probability that all 3 had correct test results, either true positive or true negative, right? Well, let's see. I can write this in this fashion, applying my multiplication rule. The probability that all 3 are correct is going to probably be the probability that the first is correct times the probability that the second is correct times the probability that the third is correct. And again, that's because we've got independent selections here, and that's because we are doing things with replacement, selecting with replacement. Alright, what's the probability that the first person chosen had a correct test result? Well, we've got 1,000 people to pick, and how many of these are correct? Well, these are the true negatives, 860. These are the true positives, so I claim there's 904 correct results in this pool. Alright, so 904 over 1,000 would be the probability that the first is correct, and because we are doing things with replacement, these fractions are going to be unchanged from first to third selection. Essentially, it's 904 over 1,000 raised to the third power, and if I punch that out on calculator, 0.904 raised to the third power, I get 0.738, I'll call it 0.739. And that's part A. Alright, now part B, they ask the same question, well, without replacement. Let's see. Make a note of that. Without replacement. So what's the probability that all 3 are correct in that case? Well, I claim it's going to be the probability that the first is correct times the probability that the second is correct. Well, assuming the first has already been chosen correct, you've got one less to choose from and one less correct response to choose from. And similarly, if the first 2 have been chosen correct, the probability the third one is correct, you've got one less to choose from, 998 divided into 902. Alright, so 904 times 903 times 902 over 1,000 times 99 times 98. And if we punch this out, we get, well, we essentially get the same answer, at least to 3 decimal places. And notice we could have used the 5% guideline here. We can use the 5% guideline. In other words, we can assume independent events. We can assume things are selected with replacement because our sample size, which was 3, is not more than 5% of the total pool, 1,000 people to choose from. Well, what's 5% of 1,000? 10% is 100, 5% is 50, and certainly 3 is not more than 50. Okay? So notice, at least to 3 decimal places, these answers are the same. Okay? Alright, I want to look at example 5. Or is it exercise? Yes, example 5 on page 162 in our text. talk about redundancy. Let me turn there. And you might want to turn there as well. Airbus 310, redundancy for better safety. Basically, well, let me read the problem. Modern aircraft are now highly reliable, and one design feature contributing to that reliability is the use of redundancy. Basically putting in redundant systems, redundant components, in case one of them goes wrong. For example, the Airbus 310 twin-engine airliner has 3 independent hydraulic systems, so that if one system fails, full flight control is maintained with another functioning system. For this example, we will assume that for a typical flight, the probability of a hydraulic system failure is 0.002. So the probability of hydraulic system, well, I'll just abbreviate it like this, hydraulic failure is 0.002. That's for one hydraulic system. Okay? And they ask in part A, if the Airbus were to have one hydraulic system, what is the probability that it would work for a flight? Right, so for one system, we want the probability that the hydraulic system will work. Well, of course, these are complementary events here. So the probability that a hydraulic system works is then 1 minus 0.002, which would be 0.998, which is a pretty high probability. But I think we can do better if we install a redundant system. That's what Part B is all about. Let's look at Part B. Given that the Airbus 310 actually has 3 independent hydraulic systems, what is the probability on a typical flight control can be maintained with a working hydraulic system? So let me write that down. If the plane has 3 hydraulic systems, all independent of each other, find the probability on a flight the book words it like this, control can be maintained by or with a working hydraulic system. Okay, well, we've got 3 of them here. Well, I think it goes like this. The probability that you can maintain control with a working hydraulic system, I'll abbreviate it like this, a working sys. Well, it's going to be 1, take away the probability that you've got a hydraulic failure in all 3 of the components, right? Well, I can write that in this way. It's 1 minus the probability that all 3 fail. Those are certainly complementary events. Well, the probability that all 3 fail, well, the probability that 1 fails is going to be 0.002. And the probability that all 3 fail are going to be 0.002 to the 3rd power by the multiplication rule. Alright, if I grind this out, punch it into my calculator, I get 0.9999992, and I can see I get a quite significantly better probability that this plane is going to travel safely than with just 1 hydraulic system. Better with redundant systems. Okay? Alright. I want to look at number 27 in our homework list, then we'll call it a day. Get a fresh screen. This is number 27 on page 167. And let's read the problem. Road rage. In a Prince Market Research survey of 2,518 motorists, write that down, 252 said they made an obscene gesture in the previous month. So 252 said they made an obscene gesture. I'll abbreviate that like so. Part A asks, if one of the surveyed motorists is randomly selected, what is the probability that this motorist did not make an obscene gesture in the previous month? So that's easy enough. I'll say the probability we randomly select one, pick one randomly, the probability that one did not give an obscene gesture. Well, of course, that's going to be 1 minus the probability of an obscene gesture, right? Well, I can perhaps more easily grind that out. Say if you've got 2,518 to choose from, the probability of not being obscene is going to be that 2,518 minus 252. So I've got 2,518 total, take away 252, and I get 2,266. Alright, so 2266 divided by 2518. I'll call it, my calculator says 0.89999. I'm going to call it 0.900, rounding off. That's alright. Alright, so not much multiplication rule there. Part B is perhaps more interesting if 50 of the surveyed motorists are randomly selected without replacement. So 50 selected without replacement. What is the probability that none of them made an obscene gesture in the previous month? So I'll abbreviate it like this. The probability that 50 are not obscene. Well, by the multiplication rule, I guess I could say it's the probability that the first one is not obscene times the probability that the second one is not obscene, but I've got to grind that out 50 times if I approach the problem in that fashion. Alright, the book tells us to do it without replacement, but I'm going to invoke the 5% guideline. I'll say 50, that's the sample that we chose, is not more than 5% of 2518. Is it not? All right. Well, let's see. 5% of 2518, 10% is 251. 5% is half of that, 125, and 50 is certainly not more than 5% of this value. So what I'm saying here, it's okay to assume things are done with replacement. And that makes things a lot easier to handle in this 50 pool. Alright, so the probability that 50 are not obscene, have not given an obscene gesture, is going to be the probability that 1 is not obscene. And we saw from part A, that's 2266 divided by 2518, raised to the 50th power. And if I punch that out on my calculator, I get 2266 divided by 2518, and I raise that number to the 50th power. I get 0.00513, I'll call it. 00513. And that's certainly much easier to arrive at than taking this fraction and knocking down the numerator and denominator down by 1 for each factor, and then multiplying all those 50 fractions together. Alright, so learn to appreciate when to apply this 5% guideline. It certainly saves a lot of ink, particularly when you're talking about pools of in the order of 50. Alright, I'm going to call it a day. We're at the 45-minute point. This concludes section 4.4, multiplication rule basics.